Hey guys, so today I will be talking about Cohen's Kappa. So what Cohen's Kappa is it's basically, well, it's essentially a statistical measure of agreement, right? So Cohen's Kappa, it measures the agreement between two raters. So we have, we can have one person and then another person, which make up those two raters. Now, basically, what that agreement helps to do is it basically helps to suggest how well these two people agree on the same result. So agree on the same result because you can't have agreement on different results, right? So, um, you know, if we go for an example. So let's say we had asked the two sort of raters to rate 10 movies. Okay, so we would have the movies. We would have 1, 2, 3, all the way to 10. Then we would have person 1. In this case, let's call that person 1 person A, and we'd have person B person 2, and let's call that person 2 person B. And between people, each person has their own sort of opinion on how they might find something, what their opinion is on that thing. So let's say, for example, for movie 1, the person A. So if we take that rating from, let's say each person can rate between 1 to 5. Let's say person A found movie 1 really boring, so let's say they found it a 1. Person B found it somewhat interesting, so they gave it a 3. Okay, person A found the next movie really fun. Person B found the next movie okay, so let's say they gave it a 4. And this would go on until there's no more sort of movies to rate. Now in this case, you can note that over here they both agreed on this result, right? On the 10th movie, they both found the movie the same level of interesting, which in this case was a 2, which indicates that the level of interest is not much. So yeah, essentially what Cohen's Kappa does is it measures agreement. Yes, it does measure agreement, but what it also measures in this case, if it measures agreement, is something called inter-reader reliability. Okay, what that basically tells us is, do the sort of opinions of each of the raters, do they depend on each other in some way? Is there some sort of pattern, or are they similar in any sort of way? So yeah, that's what Cohen's Kappa tries to find. That's why it's especially useful. And this was one example over here. Let's talk about another example. I guess I can go a bit more sciencey over here. So let's say in the field of mammography. Okay, so for those of you who know a bit about mammography, there's that process, the screening process. But for those of you who don't, I can get into it a bit more. So mammography refers to the study of breasts and breast cancer. So for a woman, she would have to undergo this process. She goes under this process where her sort of scan is taken. So those scans, they generate sort of mammograms. Okay, so this is my attempt at drawing a few mammograms. Then you have an expert radiologist who first reviews the mammograms. So we call that expert radiologist reader 1, because that's one radiologist giving their opinion on what the classification of those mammograms are, if if there is a possible chance of cancer or not. But mainly, during the screening process, the radiologists actually give their opinion on the sort of classification of that cancer, or you might also know it as BIRADS classification, which refers to the sort of size of the breast that's taken in the image, and if that indicates a possible sign of breast cancer. But then apart from reader 1, we also have reader 2. Now it's good that we have reader 2. This is good because you know if reader 1 has one opinion, then reader 2 also has another opinion. And so basically the human, in this case reader 2 is known as is the human, but they currently in the field of technology, reader 2 is being AI is actually replacing reader 2 as of now, and that's just what they're trying to automate. So in the field of mammography, the two readers can be humans, but they can be humans, and we try compare their result using Cohen's Kappa. And then but however, the readers can also be, one of the readers, in this case reader 2, can also be an AI. So reader 1 can be human, then reader 2 can be AI. So basically it's interesting to measure the agreement between the humans and then the human and the AI. Okay, so that's basically another application of Cohen's Kappa. Okay, so now if we carry on, we can now go into how Cohen's Kappa is actually calculated. So the calculation behind Cohen's Kappa. Well, Cohen's Kappa, let me write that bit properly. Cohen's Kappa is measured from, basically it can be measured from 0 to 1. Well, okay, so yeah, if we talk about the calculation of Cohen's Kappa now, well, basically Cohen's Kappa is usually measured from, well, I wrote 0, but it's usually measured from -1 to 1, where -1 indicates agreement that's worse than expected by chance, and 1 indicates perfect agreement. But usually we can simplify that to be 0, from 0 to 1, where basically if we try to understand the scales, so if we try to understand the scale, basically anything bigger than 0.8 is almost perfect. Anything bigger than 0.6 is substantial agreement, meaning it's good. It's good. It's a good agreement. Anything bigger than 0.4 is a moderate agreement, meaning there is agreement there. There is agreement there, and it's a fair bit of agreement such that, it is something to look at into a bit more. 0.2 is fair agreement, meaning it's kind of balanced, so there's a chance of being that there's a chance of it being, there is a chance of agreement, but it can also be interpreted as not being very agreeable. Okay, and then from anything that's like between, so if I say anything that's between 0 and 0.2, we say slight agreement, or we can even come to this as say little little to no agreement. Okay, I'm writing that a bit small, but I guess I'll write that a bit better. Okay, little to no agreement. Okay, now, so that's the kind of scale. So now if I go into an example of trying to calculate, well, attempting to calculate Cohen's kappa. So let's say we had a problem sort of statement where we wanted to see, what is the measure of agreement between two readers, checking to see if there is a cat in an image. Is a cat in an image? And within that sort of problem statement, we can say, let's say there's n number of images. So let's assume for demonstration purposes, we have reader A and reader B, and we have yes, no, yes, no. So this yes no over here is for reader B. This yes no over here is for reader A. Okay. So now I would just draw something like this, like a sort of grid. And I'm just going to choose some arbitrary values, but I'm going to choose some arbitrary values. So I'm just going to say 25, 10, 15. So, I mean, optionally, to make my life a bit easier, I'll just put the total. So 25, 25, 30, and 20, okay? Now, this is where we start calculating it. So the formula for Cohen's kappa it's K, where K is the Cohen's kappa, and this K is P0. So the P0, I'll get into what each of these are. P0 minus PE over 1 minus PE, okay? P0 is the observed agreement. Okay? And PE is basically the chance of that agreement occurring. So it's basically a hypothetical agreement. It's a hypothetical agreement. Okay? So now we have this example up here. What I'm going to do, actually, just so I can help you guys a bit more, is I'm going to copy this. This is why I like technology. Now I'm just going to kind of come down here and paste, okay? And just move this over here, okay? Hopefully that's better for you guys. Okay, so yeah, that's that. So this is our sort of problem statement over here. Remember, it's checked to see what is the measure of agreement between if there's a cat in a set of images. Okay, so then now if we start calculating it, well, we calculate P0 by just checking to see, basically it's just the number of true positives. So you just look at the diagonal. If you know how to interpret confusion matrices, this is very helpful here, because here essentially what we're saying is how many yeses are there, or how many no's are there. So it's just 20 plus 15 because it's no, so we use plus, and then we just do the summation of everything else. So 20 plus 5 plus 10 plus 15. Well, that's just 35 over, so just 35 over 50. So that's just 0.7, okay? That's 70% chance. Or sorry, yes, that's a 70% chance of, yes occurring or no occurring, okay? And now we can calculate the individual probabilities. So what is the probability of yes? Well, the probability of yes is just going to be the probability of yes for reader A and probability of yes for reader B, okay? So for reader A, yes is that's 25 over 50. because 20 plus 5 is 25 divided by all the divided by all the cells. And then so this is for reader A. I'm just going to say RA. And then for reader B, that's just going to be 30 over 50. Okay, and this is for reader B. Okay, so a small mistake I wrote over here is I wrote plus. This should be times, because we're saying, because this probability of yes is made up of the probability of reader A saying yes and probability of reader B saying yes. So this is just equal to 0.5 times 0.6, which is 0.3, or 30%. Okay. Similarly, we do the same for no. I think I'm going to skip straight to the sort of overall probability, but that's just 0.5 times 0.4, and that's just equal to 0.2. Okay, so we have 20%. It's for reader A, this is for reader B. Okay, so now we have our probabilities. We have the observed probability, we have the probability of a yes occurring, that there is a cat in the image, and probability of no occurring, that there isn't a cat in the image. Remember, our formula is K is equal to, it's up here but I'll write it again, K is equal to P0 minus PE, 1 minus PE. So it's the probability, the observed agreement, so the probability of observed agreement, take away the probability of hypothetical agreement, divided by the 1 minus the probability of hypothetical agreement. Okay, so it's just a ratio essentially. And so the probability of hypothetical agreement now is just going to be the probability of yes plus the probability of no. Okay, so that's just going to be 0.3 plus 0.2, which is 0.5. So this is a 50% chance that essentially they agreed on yes or no. So agreed on yes or no. The chance that they agreed on yes or no. Okay, now if we apply our Cohen's kappa to this, so P0, I'm going to write the formula again just so it sticks with you guys. Okay, so what is our P0? Our P0, or I should say our observed agreement, is 0.7. Okay, so that's 0.7. What is our hypothetical agreement? Well, that's 0.5. So I think if I highlight them, it will maybe help you guys a bit more. So 0.7 and hypothetical is 0.5. I can highlight the probability of yes in yellow and probability of no in green. Okay, so 0.7 minus 0.5. Oh, I think I should switch back to black just so it's nicer and more consistent. And then that's just 1 minus the hypothetical agreement. Okay, so K is equal to 0.2 divided by 0.5, and that's just, well, that's just 0.4. Okay, because 20% divided by 50%, you know, well, 20 over 100 divided by 50 over 100, that will give you 40 over 100, so 0.4. Well, what is the 0.4 then? Well, if we go back up to our scale, 0.4 represents a, well, we can say here it represents a moderate agreement. So that means for this problem statement that there's a moderate agreement between reader A and reader B, and hence we can interpret that as that being agreement that we should look into. And yeah, not saying that you shouldn't look into a fair agreement or even slight or little to no agreement, but then if it's, you know, I think out of the scale, moderate agreement, when it comes to moderate agreement, it's at that point where you question whether it's substantial enough for you to make inferences from that or not, and that's why you have to do a bit more research into that sort of data. So yeah, that's basically it. So I hope that made sense for you guys. Yeah, so this was just Cohen's kappa. Just a quick small recap on what Cohen's kappa is. It's the agreement between two raters. One thing I didn't mention is, well, what if there's more than two raters? Well, then you just use Fleiss's kappa instead. Okay, Fleiss's kappa. But yeah, it's agreement between two raters, and it just see if they agree on the same result, and if there's inter-reader reliability, such that, you know, do the results kind of depend on themselves to increase that agreement. And Cohen's kappa will only work on categorical, not categorical variables where those variables are nominal. Okay, so nominal. So this will only work for discrete data, and that data has to be categorical. Okay, it won't work on continuous data. So yeah, this is a very important point, so please do remember this. And yeah, I hope you guys enjoyed this, and I think there's going to be some more to come, with a few more sort of concepts, and yeah, I'll see you guys later.